What is common between Vedic math and divisibility rules? These might look so different, like chalk and cheese, but there's actually something common between that. The commonality is nothing but patterns. Patterns that turn into rules. I'm not saying this is true of every single sutra in Vedic math, but if you see some of them, it's essentially patterns that we have observed in math which have been turned into rules. Similarly, in divisibility rules, we look at patterns in number systems and then apply those rules. Now, the reason I'm doing this video is to some extent let you awaken your mind to the idea that you don't want to just remember these rules by rote. Right? Rote memorization is not the way forward, but rather to spend some time experimenting with these numbers, with these patterns, and understand the truth behind it, and then try to remember these rules sans memorization. You wouldn't have to memorize because you would just know the rules. So let's get a little concrete here. Let's try and do something very specific. Okay, so for example, let's think about the divisibility rule for 3. Divisibility for 3. Now, what's the divisibility rule for 3? You take all the digits, you add them together, and if that sum, you recursively add it, and if that sum is divisible by 3, then the number, the whole number itself is. So, for example, if I were to ask, is 96 divisible by 3? You would say yes, 9 plus 6 is 15, which is also 2 digits. 15 would kind of translate to 1 plus 5, 1 plus 5, which is 6, and 6 is divisible by 3. Right? So, in other words, what we're doing here is we made this observation about all the numbers that's divisible by 3, and we said, okay, there seems to be a pattern. Just add the digits together, and if that addition is a number which is divisible by 3, which is either 3, 6, or 9, when you recursively do it, then that should be divisible by 3, which is fantastic. The problem is it works only for the decimal number system. Does that mean there's other number systems? Yes, there is. So let's kind of think about, okay, so what are the other number systems? So for example, numbers can be represented in different bases. It could have a completely different way in which we represent, for example, the Roman system, in which this rule might not work. So let's try and spend some time understanding it. So what I've done is I've written down all the numbers from 1 to 22 in different systems. So the Roman system is where you use letters like I for 1. So 2 becomes 2 I's, 3 becomes 3 I's. But 4 is slightly different. You take IV, which is essentially V stands for 5. I on the left basically means 1 less than 5. And therefore it is IV. So this is a system in itself. Now, obviously, if you look at all the multiples of 3 here, it's very hard to find a pattern, right? You might not be able to see a pattern at all. And it's very hard to say that this would mean divisible. And that's one of the reasons why, in general, we have moved away from systems like Roman systems. What about something that's base 9? Now, what's base 9? Base 9 is where you have only 9 possible digits, 0 to 8. A decimal system is when you have 0 to 9. So there's 10 different types of digits which recombine. So the moment we move into a number that's 1 more than 9, you don't have a symbol to represent the 10. And therefore, you create a place system. And you reuse the very first digit, which is essentially 1. And you say 1, 0 is 10. And we've kind of completely understood it. But in case of base 9, you don't have a 9 at all. You have only the numbers from 0 to 8. So when you come to 9, you need to create a place system, and 9 actually looks as 1 0. You don't call it 10. In the 9 base system, this is actually 9. 1 1 is 10, 1 2 is 11, 1 3 is 12, 1 4 is 13, so on. 1 8 is 17. And when you come to the actual 18, the number 18 in the decimal system, that becomes 2 0. Now, if you were to try and apply a similar rule here to think about divisibility by 3, it completely fails. However, it's very interesting to see what happens when you think about divisibility by 2. Right? So in case of decimal systems, you know that every digit that ends in the number 2, 4, 6, 8 or 0 is going to be divisible by 2. But in the case of base 9, you would realize that that fails. Right? So that kind of fails because you don't have the numbers ending in that particular value. However, you would see that there's a new pattern here. If you add the digits here, and if those addition of those digits end up in 2, 4, 6, 8 or 0, then it's divisible. So in other words, the divisibility rule for 3 in decimal system is very similar to the divisibility rule for 2 in the system where for base 9 number systems. Right? Similarly, you can think of it for binary systems. If you see all the even numbers in binary system or the odd numbers in binary system, they end in 0. So the even numbers end in 0, the odd numbers end in 1. This is very similar to looking at divisibility of rule 5 in decimals, where the number ends only in the same digit, either 2 or 0, or very similar to the odd numbers and even numbers as well. All right. So are there other patterns? Definitely there must be. And if you were to take up a separate base system, like a base 8 system or a hexadecimal system, and play around with the same kind of divisibility rules, then you will be able to unearth patterns which will then create new divisibility rules for you. And that's the kind of experimental math that I would suggest that a student of math like you should be doing. Right? Don't take up these rules and try to remember them by rote, but rather try and see similarities and patterns and the differences between systems to really understand why certain things exist the way they are. And that would definitely expand your mind and make you appreciate number systems and math in general, and really enjoy the beauty behind it. I hope you found this video useful and helpful. If so, please share it with your friends and family. Subscribe for more such videos, and don't forget to click on the bell icon so that YouTube will remind you the next time I'll be posting a video. Thank you so much. Have a great day.